Today, the date is November 16th, 2023. It is currently 9:01 a.m. Today, Chapter 47 of the Modern Automotive Technology by James E. Duffy. Cooling System Technology. Objectives. After studying this chapter, you will be able to summarize the functions of engine, supercharger / turbocharger, and HV or hybrid vehicle cooling systems. Explain the operation and construction of major cooling system components found in modern vehicles. Compare cooling system design variations. Explain the function of antifreeze. Compare hybrid air and liquid or water cooling systems. Correctly answer ASE certification test questions on cooling systems found in modern passenger vehicles. Technical terms of this chapter include antifreeze, bypass thermostat, bypass valve, closed cooling system, coolant temperature sensor or CTS, electric cooling fan, engine cooling system, engine operating temperature, engine temperature gauge, fan spacer, flexible hose, fluid coupling fan clutch, heater core, heater hose, hose clamp, hose spring, HV battery cooling system, HV battery radiator, HV motor generator cooling system, HV power control module cooling system, liquid cooling system, molded hose, motor generator cooling system, petcock, radiator, radiator cap pressure valve, radiator cap vacuum valve, radiator core, radiator filler neck, radiator shroud, radiator tank, supercharger cooling system, temperature warning light, thermostat, thermostat rating, thermostatic fan clutch, transmission oil cooler, turbocharger cooling system, water pump housing, water pump hub, water pump impeller, water pump shaft, and worm drive hose clamp. This chapter begins by explaining the design, construction, and operation of engine cooling systems. Supercharger and turbocharger intercooler systems are then presented. Finally, hybrid cooling systems for the high voltage HV battery, HV power control module, and hybrid motor generator are discussed. You must fully understand how different cooling systems work before learning to service and repair them. Vehicle cooling systems. A passenger vehicle can have several cooling system types, each designed to control the operating temperature of a mechanical and electrical assembly. Today's vehicles generate internal heat during operation, including from the internal combustion engine, supercharger or turbocharger, HV battery, or HVPCM. Without a properly operating cooling system, an engine can, quote, self-destruct in a matter of minutes. Internal engine parts can overheat and partially melt, causing the engine to seize, or reciprocating assembly no longer rotates freely. Specific cooling systems. An engine, supercharger, turbocharger, battery pack, motor generator, and high power control circuit must not get too hot or damage will result. During startup, a cooling system must help the assembly warm to operating temperature quickly to lower emissions and wear. After the assembly has warmed up, the cooling system must maintain a constant operating temperature to prevent overheating. The following are the most common types of cooling systems found on modern gas, diesel, hybrid, and electric drivetrains. Engine cooling system, supercharger cooling system, turbocharger cooling system, HV battery cooling system, HV motor generator cooling system, HV power control module cooling system. Engine cooling system. An engine cooling system controls the operating temperature of the cylinder heads and cylinder block. It must warm the aluminum and steel engine quickly without exceeding the factory specified operating temperature. It must also provide a means for warming the passenger compartment in cold weather. Supercharger cooling system. A supercharger cooling system must cool the air before it enters the engine to increase power and efficiency. When air is compressed, the air is heated almost to the ignition point of gasoline. If the engine intake air is too hot, the air-fuel charge can detonate and explode. To prevent this, a supercharger cooling system forces a liquid coolant through an intercooler, or heat exchanger, mounted under the supercharger. Turbocharger cooling system. A turbocharger cooling system forces coolant through the turbo bearing housing to keep the turbo from overheating under prolonged high boost. Because it is compressing air entering the engine and carrying hot exhaust gases blowing over the turbine wheel, excessive heat can make the turbo housing glow red hot. A turbocharger cooling system prevents heat from burning up turbo seals, bearings, or the turbine wheel. HV battery cooling system or hybrid vehicle. An HV battery cooling system uses air or a liquid to remove battery cell heat when under prolonged high amperage draw. Most vehicles use an electric motor, blower, fan to force outside air through the battery pack. Housing to keep it cool. The warm air is then exhausted through ducts. The electric drivetrains of high-power hybrids force coolant into and between the battery pack modules to prevent overheating damage to the plates in the cells. Air cooling may not be sufficient with super high watt-hour HV batteries. Let me reread that. Air cooling may not be sufficient with super high watt-hour HV batteries. HV motor generator cooling system. An HV motor generator cooling system uses liquid coolant to prevent motor generator overheating in full electric and hybrid gas electric vehicles. Coolant lines run through the stator housing. With plug-in hybrids, the motor generator can operate for 50 miles or 80 kilometers under all-electric propulsion, which generates high temperatures. The circulation of liquid coolant carries the motor generator heat to a heat exchanger or to the engine cooling system. HV power control module cooling system. An HV power control module cooling system forces air or a liquid through or over the HV power control module housing. When an HV power control module circuit gets too hot, power transistors can go into thermal runaway, capacitors and resistors can burn, and printed circuit boards can fail. The HV power control module generates tremendous amounts of electrical energy and heat, which must be controlled. Engine cooling system functions. An engine cooling system performs several functions: removes excess heat from the engine's assembly, maintains constant engine operating temperature, helps a cold engine quickly reach operating temperature, provides a heat to the heater or climate control system, which uses the heat to warm the air in the passenger compartment. Removing engine heat. Most combustion heat is used to produce expansion and pressure for piston movement. However, some combustion heat flows out with the exhaust gases or flows into the metal parts of the engine. An engine can overheat and be seriously damaged in a matter of minutes if excess heat is not removed. The burning air-fuel mixture produces a tremendous amount of heat. Combustion flame temperature can reach 4,500 degrees Fahrenheit or 2,500 degrees Celsius. Iron melts at around 2,750 degrees Fahrenheit or 1,510 degrees Celsius. Steel melts at around 2,500 degrees Fahrenheit or 1,370 degrees Celsius. Aluminum melts at even lower temperatures, 1,220 degrees Fahrenheit or 660 degrees Celsius. The combustion flame is similar to the blast of fire blown out by an oxyacetylene cutting torch. Oxyacetylene cutting torch. Imagine the potential catastrophic damage to the engine if some of this heat is not removed from soft aluminum and plastic engine parts. Maintaining engine operating temperature. Engine operating temperature is the temperature the engine coolant, or water and antifreeze mixture, reaches under normal running conditions. Typically, an engine's operating temperature is between 180 degrees Fahrenheit and 210 degrees Fahrenheit, or 82 degrees Celsius and 99 degrees Celsius. When an engine warms to operating temperature, its parts expand. This ensures that the clearances are correct for the expanded parts. It also ensures proper combustion, lower emission output levels, and good engine performance. Reaching engine operating temperature quickly. An engine must warm up rapidly to prevent poor combustion, part wear, oil contamination, reduced fuel economy, increased emissions, and other problems. For example, the aluminum pistons in a cold engine are not expanded by heat. As a result, there is too much clearance between the pistons and the cylinder walls. Additionally, the oil in a cold engine is very thick, which can reduce engine power. The air-fuel mixture does not vaporize and burn as efficiently in a cold engine. An engine cooling system must allow the engine to warm up quickly to minimize these negative effects. Heater operation. A cooling system commonly circulates coolant to the passenger compartment heater. The heater core is a small liquid-to-air heat exchanger mounted under the passenger side of the dash in the passenger compartment. The heat from the engine coolant's temperature, which is around 200 degrees Fahrenheit or 93 degrees Celsius, is used to warm the passenger compartment. A heater blower fan and motor force A heater blower fan and motor force warm air out of the heater core and out the dash vents. Liquid engine cooling systems. A liquid cooling system circulates coolant, a solution of water and antifreeze, through the water jackets in the engine cylinder block and cylinder heads. The coolant collects excess heat on metal parts and carries this heat away from the engine. Closed cooling systems. A closed cooling system uses an expansion tank or reservoir and a radiator cap with pressure and vacuum valves. The overflow tube is routed into the bottom of the reservoir tank. Pressure and vacuum valve action pull coolant in and out of the reservoir tank as needed. This keeps the cooling system correctly filled at all times. When the engine heats up, the coolant expands and opens the cap pressure valve. Instead of leaking onto the ground, the coolant flows into the reservoir. After the engine has been shut off, the coolant temperature drops and its volume decreases. This causes the vacuum valve to open. Atmospheric pressure or system suction then forces coolant back into the radiator. This compensates for any small system leaks, keeping the system properly filled. Cooling system parts. Cooling system parts. The basic parts of an engine cooling system are water pump, radiator hoses, radiator, fan, thermostat. When the engine is running, the water pump forces coolant to circulate through the engine water jackets or internal passages in the engine. While the engine is cold, the thermostat remains closed, so coolant circulates inside the engine but not the radiator. This helps warm the engine quickly. When the engine reaches operating temperature, the thermostat opens. Heated coolant then flows through the radiator, where excess heat is transferred from the hot coolant to the cool air flow through the radiator. Water pump. The engine-driven water pump is an impeller or centrifugal pump that forces coolant through the engine block, cylinder head, intake manifold, hoses, and radiator. It is often driven by a belt running off the crankshaft pulley. In some cases, the pump is gear-driven directly off the crankshaft sprocket and timing chain. The major parts of a typical water pump include the following. The water pump impeller is a steel or plastic disc with straight or curved fan-like blades that spins and produces pressure and flow. Straight blades are sometimes used to reduce engine power consumption. A water pump shaft is a steel shaft that transfers turning force from the hub to the impeller. The water pump seal prevents coolant from leaking between the pump shaft and pump housing. Water pump bearings are plain or ball bearings that allow the pump shaft to spin freely in its housing. The water pump hub provides a mounting place for the belt pulley and fan. The water pump housing is an aluminum casting that forms the main body of pump. A water pump gasket fits between the engine and pump housing to prevent coolant leakage. RTV sealer or rubber seal may be used instead of a gasket. The water pump typically mounts on the front of the engine. With some transverse or sideways mounted engines, it bolts to the side of the engine and extends toward the front. Water pump operation. The spinning engine crankshaft pulley turns the drive belt, which turns the water pump pulley, pump shaft, and impeller. The coolant trapped between the impeller blades is thrown outward by centrifugal force. This produces suction or vacuum in the central area of the pump housing. It also produces pressure in the outer area of the housing. Since the pump inlet opening is near the center, coolant is pulled out of the radiator through the lower hose and into the pump. After being thrown outward and pressurized, the coolant flows into the engine. It circulates through the block, around the cylinders, up through the cylinder heads, through the thermostat, and back into the radiator. Electric water pump. An electric water pump uses a DC motor and an impeller to force coolant through the engine's water jackets or through the HV cooling system. It replaces a belt-driven water pump. The electric water pump's assembly often bolts to the side of the engine and has one radiator hose connected to it. When the engine control module senses that the engine has reached a predetermined operating temperature, it energizes the electric water pump. The resulting coolant flow maintains the correct engine temperature. Since the electric water pump does not operate until needed, it allows the engine to reach operating temperature more quickly for improved efficiency. The speed of the electric water pump can also be controlled by the ECM to reduce energy consumption. Radiator and heater hoses. Radiator hoses carry coolant between the engine water jackets and the radiator. These flexible hoses can withstand engine vibration without breaking. The upper radiator hose usually connects to the thermostat housing on the intake manifold or cylinder head. Its other end fits on the radiator. The lower hose often connects the water pump inlet and the radiator. A molded hose is manufactured in a special shape with bends to clear the cooling fan and other parts. A replacement hose of the same shape must be purchased to fit the year, make, and model of the vehicle being serviced. A flexible hose has an accordion shape that allows it to be bent to different angles. The pleated construction allows the hose to bend without collapsing and blocking flow. A flexible hose is also called a universal type radiator hose. A hose spring is frequently used in the lower radiator hose to prevent the hose from collapsing. The lower hose is exposed to suction from the water pump. The spring ensures that the inner lining of the hose does not tear away, close up, and stop circulation. Caution: never remove the spring from inside a radiator hose. The hose can collapse and cause engine overheating if the spring is removed. Heater hoses are small diameter hoses that carry coolant to the heater core under the dash. Hose clamps hold the radiator hoses and heater hoses on their fittings. A worm drive hose clamp uses a worm gear that engages slots in the clamp strap to allow tightening around the hose. Caution: avoid using worm drive hose clamps on plastic fittings in the cooling system. They do not clamp the hose evenly and can crack plastic hose fittings. Radiator. The radiator transfers coolant heat to the outside air. The radiator is normally mounted in the front of the engine where cool outside air can flow freely through the grill. A radiator typically consists of 6 components. The radiator core is the fragile center section of a radiator that is made up of aluminum tubes and cooling fins soldered or bonded together. Heat from the coolant is transferred to the air flowing around the coolant-filled tubes in the core. Radiator tanks are the metal or plastic ends that fit over the core tube ends to provide storage for coolant and fittings for hoses and lines. The radiator tanks have fittings for large coolant hoses and sometimes small fittings for transmission oil coolers. A removable radiator pressure cap locks onto the radiator filler neck, allowing the system to build pressure, which increases the boiling point of the coolant. The radiator neck also has an overflow tube connected to the coolant reservoir tank. A transmission oil cooler is an inner tank for cooling automatic transmission or transaxle fluid. It is located inside the radiator tanks and has tube fittings for the metal cooler lines running back to the transmission. The radiator petcock is a fitting on the bottom of the tank for draining coolant. The radiator cap pressurizes the water and antifreeze solution so that it does not boil during engine operation. Transmission oil cooler. A transmission oil cooler is often placed in the radiator on cars with automatic transmissions or transaxles to prevent the transmission fluid from overheating. It is a small tank enclosed in one of the main radiator tanks. Heat is removed from the transmission fluid, which is hotter than the engine coolant, as it passes through the radiator and cooler. Line fittings from the cooler extend through the radiator tank to the outside. Metal lines from the automatic transmission or transaxle connect to these fittings. The transmission oil pump forces the fluid through the lines and cooler. Radiator cap. The radiator cap performs several functions. Seals the top of the radiator filler neck to prevent leakage. Pressurizes the system to raise the boiling point of the coolant. If the coolant boiled, it would turn to steam that would blow out the radiator cap overflow. Relieves excess pressure to protect against system damage. Allows coolant flow between the radiator and the coolant reservoir as the engine warms or cools. The radiator cap locks onto the filler neck or on the reservoir tank. Rubber or metal seals make the cap to neck joint airtight. Radiator caps can be made of metal or plastic. Radiator cap pressure valve. The radiator cap pressure valve consists of a spring-loaded disc that contacts the filler neck. The spring pushes the valve into the neck to form a seal. Typical radiator cap pressure is 12 to 16 psi or 83 to 110 kPa. This pressure raises the boiling point of the engine coolant to 250 degrees Fahrenheit to 260 degrees Fahrenheit or 121 degrees Celsius to 127 degrees Celsius. Many surfaces inside the engine's water jackets can be above 212 degrees Fahrenheit or 100 degrees Celsius, because the flame of combustion can burn at several thousand degrees. If the engine overheats and pressure exceeds the cap rating, the pressure valve opens. Excess pressure and steam force the coolant out of the overflow tube and into the reservoir. This prevents high pressure from rupturing the radiator, gaskets, seals, or hoses. Radiator cap vacuum valve. The radiator cap vacuum valve opens to allow flow back into the radiator when the coolant temperature drops after engine operation. It is often a small valve located in the center of the bottom of the cap. The cooling and contraction of the coolant and air in the system decreases the coolant volume and pressure. Without a cap vacuum valve, the radiator hoses and radiator tanks could collapse from outside pressure. Cooling system fans. A cooling system fan pulls air through the core of the radiator and over the engine to help remove heat. It increases the volume of air flowing through the radiator, especially when the car is standing still. The fan is driven by a fan belt or an electric motor. Engine-powered fans. An engine-powered fan bolts to the water pump hub and pulley. Sometimes, a fan spacer fits between the fan and pulley to move the fan closer to the radiator. A fluid coupling fan clutch is designed to slip at higher engine speeds. The clutch is filled with silicone-based oil. At a specific fan speed, there is enough load to make the clutch slip. A thermostatic fan clutch has a temperature-sensitive bimetal spring that controls fan action. The spring controls oil flow in the fan clutch. When cold, the spring causes the clutch to slip, speeding engine warm-up. After reaching operating temperature, it locks the clutch, providing forced air circulation. Electric cooling fans. An electric cooling fan uses an electric motor, the engine coolant temperature sensor, and an ECM to provide airflow and heat transfer out of the radiator. An electric fan or fans are needed on front-wheel drive cars with transverse-mounted engines. In these vehicles, the water pump is normally located away from the radiator. Nevertheless, electric engine fans can be used on any engine or transmission layout. The fan motor is a small DC motor with brushes. It requires 12-volt DC for operation. It mounts on a bracket secured to the radiator. A plastic fan blade mounts on the end of the motor shaft to create airflow when the vehicle is not moving. An electric fan saves energy and increases cooling system efficiency. Because the fan functions only when needed, it helps speed engine warm-up. This reduces emissions and fuel consumption. In cold weather, the electric fan may shut off at highway speeds because enough cool air is rushing throughout the grill to provide adequate heat removal. Electric engine fan circuits. In late model vehicles, the coolant temperature sensor, or CTS, switcher variable resistor, fuse box relays, and engine ECM operate the engine cooling fan motors. When the engine is cold, the coolant sensor and ECM do not energize the fan relay. This keeps the cooling fan from energizing and spinning unnecessarily. After warm-up, the engine temperature sensor resistance changes to signal the ECM for cooling fan operation. The ECM sends current to the fan relay coil. This closes the relay contact points, and high current flows to the cooling fan motors to prevent engine overheating. A CAN wiring diagram for an ECM controlled fan circuit is illustrated in figure 47-11. I usually try to avoid reading the figure 47-11 because this is an audiobook, and I'm not going to be able to refer to that shit when I'm listening. If I am reading the book and listening, then I'll have it right there, but for anybody that doesn't have the book, that could be kind of confusing. Oh, figure 47-11. Yeah, I don't have that, says the person listening to this without the book. But they tricked me on this one. Radiator shroud. The radiator shroud that surrounds the fan helps ensure that the fan pulls air through the radiator. It fastens to the rear of the radiator and surrounds the area around the fan. When the fan is spinning, the plastic shroud keeps air from circulating between the back of the radiator and the front of the fan. As a result, a huge volume of air flows through the radiator core. Without a fan shroud, the engine could overheat. Thermostat. The thermostat expands and contracts with changes in engine temperature and controls coolant flow through the radiator. It reduces coolant flow when the engine is cold and increases coolant flow when the engine is hot. The thermostat normally fits under a thermostat housing between the engine and the end of the upper radiator hose. The thermostat has a wax-filled pellet contained in a cylinder and piston assembly. A spring holds the piston and valve in a normally closed position. When the thermostat is heated, the pellet expands and pushes the valve open. As the pellet and thermostat cool, spring tension overcomes pellet expansion and the thermostat valve closes. A thermostat rating is stamped on the thermostat to indicate the operating or opening temperature of the thermostat valve. Normal ratings are between 180 degrees Fahrenheit and 195 degrees Fahrenheit, or 82 degrees Celsius and 91 degrees Celsius. High thermostat heat ranges are used in automobiles because they reduce exhaust emissions and increase combustion efficiency. Thermostat operation. When the engine is cold, the thermostat is closed and coolant cannot circulate through the radiator. Instead, the coolant circulates around the inside of the engine block, cylinder head, and intake manifold until the engine is warm. As the heat range of the thermostat is reached, the hot engine coolant causes the pellet inside the thermostat to expand. The thermostat gradually opens and allows coolant to flow through the system. Since the amount that the thermostat opens is dependent on engine temperature, the exact operating temperature of the engine can be precisely controlled. A bypass valve and a bypass hose, or passage, permit coolant circulation through the engine when the thermostat is closed. If the coolant cannot circulate, hot spots could develop inside the engine. A bypass thermostat has a second valve for routing all the hot coolant through the radiator, not just most of the coolant. The main thermostat valve regulates flow through the engine and radiator like a conventional thermostat. The bypass valve blocks off the bypass once the engine has reached operating temperature to reduce pumping losses. Cooling system instrumentation. Most vehicles are equipped with a temperature warning light. Some vehicles also have an engine temperature gauge. It is important that you understand the operation of both. Temperature warning light. A temperature warning light informs the driver when the engine is overheating. When the coolant becomes too hot, a temperature sending unit or switch in the engine block closes. This completes the warning light circuit, and the indicator light on the dash glows. With many late model vehicles, the engine temperature warning light is energized by the engine control module. If the sensor detects an overheating engine, the ECM sends its current to the dash warning light. When the engine is cold or at normal operating temperature, the sending unit is open and the light remains off. When the ignition switch is rotated one notch to run, or not all the way to start, the instrumentation ECM illuminates all of the dash warning lights so the driver knows that they are all functioning. Engine temperature gauge. An engine temperature gauge shows the exact operating temperature of the engine coolant. A variable resistance sending unit and a gauge are often used in the circuit. When the engine is cold, the gauge sending unit has a high resistance, so little or no current flows through the gauge circuit. The temperature gauge reads cold. As engine temperature increases, the resistance in the sending unit drops. Current increases in the gauge circuit. Higher amps make the gauge needle deflect to the right, showing engine temperature. On vehicles equipped with a powertrain ECM and instrumentation ECM network, the network commonly operates the engine temperature gauge using primarily the signal from the engine temperature sensor. Antifreeze. Okay, I'm gonna repeat myself because it stopped recording. Okay. Antifreeze. Usually ethylene glycol is mixed with water to produce engine coolant. Antifreeze has several functions. It prevents winter freeze-up, prevents rust and corrosion, lubricates the water pump, and cools the engine. Antifreeze keeps the coolant from freezing in very cold weather, below 32 degrees Fahrenheit or 0 degrees Celsius. Coolant freezing can cause serious cooling system and engine damage. As ice forms, it expands. This expansion can produce great force. Internal ice formation may crack the water pump housing, cylinder head, engine block, radiator, or other parts. Antifreeze prevents rust and corrosion inside the cooling system. It provides a protective film on part surfaces. Even in hot climates, antifreeze should be used to protect internal parts from corrosion. Antifreeze also lubricates the water pump and thermostat. It increases the service life of the water pump bearings and seals. It also prevents thermostat wear and corrosion. Antifreeze conducts heat better than water and, therefore, cools the engine better. Using the air conditioning system, for example, increases the temperature of the air flowing through the radiator. Antifreeze can help prevent overheating in hot weather when the air conditioning is on constantly. Antifreeze/water mixture. A 50-50 mixture of water and antifreeze is usually recommended for ideal cooling and protection from freezing. An equal mix of glycol, antifreeze, and water provides protection from ice formation to about -34 degrees Fahrenheit or -37 degrees Celsius. Higher ratios of antifreeze may prevent freezing in extreme weather conditions. Tech tip: antifreeze is available in concentrated form or pre-mixed with 50% water. If you mix your own solution, you will get twice as much antifreeze for around the same price as the pre-mixed. Caution: plain water should never be used in a cooling system instead of antifreeze. Water does not provide the same functions and protection as antifreeze. Pre-mixed antifreeze should not be mixed with additional water because the diluted antifreeze does not provide the same amount of protection. Block heater. A block heater may be used on an engine to help with engine starting in cold weather by heating the coolant. A block heater is most commonly used on diesel engines. Diesels are more difficult to start in cold weather than gasoline engines because of their compression ignition. A block heater is simply a 120-volt heating element mounted on the block water jacket. The heater power cord is plugged into a standard electrical outlet. This keeps the engine and coolant warm when the vehicle is not being used. Then, when the owner cranks the engine on a cold morning, it will start more easily. Supercharger and turbocharger cooling systems. When a supercharger or turbocharger compresses the air and builds boost pressure, the compressed air heats up. Hot air carries less oxygen for combustion than an equal amount of cooler air. A supercharger cooling system often uses its own electric water pump, hoses, and radiator to pump cool antifreeze through the supercharger intercooler. When the heated boost air flows through the intercooler fins, heat from the inlet air is transferred into the coolant and carried away. The cooler air entering the engine provides more oxygen for burning fuel. Cooler air also allows more boost pressure without engine detonation or abnormal combustion and severe part damage. Hybrid cooling systems. Plug-in hybrids with powerful battery packs and 100+ horsepower traction motors generate high heat and require cooling of major electrical assemblies. A hybrid cooling system uses circulated air or liquid coolant systems like the following to remove excess heat from components in the electric powertrain. A hybrid air cooling system uses an electric blower, fan, and a system of ducts to route cool outside air around the high voltage battery pack. The cool airflow helps pull heat from the battery packs. A hybrid liquid cooling system uses an electric water pump, small diameter hoses, and a separate radiator or heat exchanger to pull heat from the HV battery, HV, PCM, and motor generator. Low power motor generators and mild hybrids do not require an additional cooling system. When the motor generator is mounted in the transmission or rear axle assembly, the transmission cooler and transmission fluid help limit motor generator temperatures. However, high power hybrids usually require forced liquid cooling to prevent motor generator stator winding failure. HV battery cooling systems. An HV battery cooling system uses circulated air to carry heat away from the battery packs and out of the battery housing. Again, high power electric powertrains also supplement air cooling with liquid cooling. An HV battery radiator or small air to liquid heat exchanger is mounted in the battery housing. Intake air is routed through the cool fins of the radiator or heat exchanger before it circulates over the battery packs. An HV battery fan can be energized by the HV ECM to force fresh air through the air to liquid heat exchanger and over the battery pack outer surfaces for cooling. Motor generator cooling systems. A motor generator cooling system removes excess heat from the stator housing. I need to learn how to pronounce that. Stator housing and windings by circulating coolant through its outer housing. Again, High wattage, high horsepower traction motors will overheat and burn without heat removal from the stator housing. Some motor generators and PCMs use the same electric water pump and radiator to lower coolant temperature to around 100 degrees Fahrenheit or 38 degrees Celsius, which improves motor generator efficiency. Motor generator water jackets that carry liquid coolant are formed or machined inside the stator. I'm gonna look that up. It's stator. Stator. Okay. Motor generator water jackets that carry liquid coolant are formed or machined inside the stator housing during manufacture. A large water jacket is often formed between the motor generator stator housing and its outer housing for direct heat transfer into the liquid coolant. Motor generator coolant hoses carry cooled coolant to and heated coolant from the motor generator water jackets. One hose provides a flexible connection to the electric coolant pump or engine water pump. Motor generator coolant fittings allow rubber hoses to be clamped to the fittings for leak-proof connections. A motor generator water pump is an electric coolant pump mounted between the system radiator and the stator housing. HVPCM cooling systems. An HVPCM cooling system often uses the same electric water pump and circulated liquid coolant as the motor generator and HV battery use. As discussed, high-power hybrids have their own separate cooling systems to remove heat from the high-power electrical circuits and components. This cooling system is independent of the engine cooling system. A water jacket is formed between the PCM's inner and outer housings. The high-power control circuit boards are mounted on a heatsink, which is an integral part of the inner PCM housing and in contact with the coolant. Heat from the control boards passes through the heatsink and into the coolant circulating between the PCM's inner and outer housings. Tech tip: hybrids with DEFI gasoline engines do not suffer from cold start problems because only air flows past the engine intake valves and fuel is injected into the combustion chambers and cylinders directly. There is no fuel sprayed inside the intake manifold that could condense into an unburnable liquid on metal surfaces inside the manifold, cylinder head ports, and intake valve. In summary, a vehicle cooling systems must remove excess heat from the engine, maintain a constant engine operating temperature, increase the temperature of a cold engine quickly, and provide a means for warming the passenger compartment. Engine operating temperature is typically between 180 degrees Fahrenheit or 82 degrees Celsius and 210 degrees Fahrenheit or 99 degrees Celsius. The basic parts of an engine cooling system are the water pump, radiator hoses, radiator, fan, and thermostat. The radiator transfers heat from the coolant to the outside air and is normally mounted in front of the engine. A transmission oil cooler is often placed in the radiator on cars with automatic transmissions to prevent transmission fluid overheating. The thermostat senses engine temperature and controls coolant flow through the radiator. Antifreeze, usually ethylene glycol, is mixed with water to produce the engine coolant. It prevents winter freeze-up, prevents rust and corrosion, the water pump, and cools the engine. A supercharger cooling system often uses its own electric water pump, hoses, and radiator to pump cool antifreeze through the supercharger into cooler. A hybrid cooling system can use either circulated air or circulated liquid coolant to remove excess heat from electrical/electronic components in the electric powertrain. This has been Chapter 47 on Modern Automotive Technology by James E. Duffy. I am your narrator Joseph A. Cuevas. I hope you have found value in this today. The next chapter we will be covering is Chapter 49, Lubrication System Fundamentals. Alrighty, and that is it.